Hi everyone, my name is Yinzhan. I will present faster dynamic range mode. This is joint work with Bryce, Sandlund. In the dynamic range mode problem, we are asked to maintain an array A, which is initially empty. We can make two types of updates. We can either insert an element to or delete an element from the array A. Each query asks for the most frequent element in an interval of the array, and this element is called the mode of the interval. In this work, we also use the frequency of the mode as an acceptable answer to the query. This is because, as we showed in the paper, these two notions are equivalent up to polylogarithmic factors. We also guarantee that the size of the array does not exceed n at any point in execution. Here is an example. So the query for the range 2, 3, 3 has the mode 3 because 3 appears most frequently. We can also insert element to the middle of the array or delete element from array. Of course, we can still perform queries after some deletion or insertion. There are some previous works on dynamic range mode. It was known that we can do both the update and query in O tilde until 2/3 time, where O tilde in this presentation hides polylogarithmic factors. In a Chan et al. 14th paper, they shaved some log n factors from this classical algorithm, and in the Yinzhan et al. 18th paper, they removed all log n factors and achieved O until 2/3 time for both update and query. On the lower bound side, if we assume the online matrix vector multiplication conjecture, which is a popular conjecture in fine-grained complexity, then no data structure can run in O into the 1/2 minus epsilon time for positive epsilon. This is implied by the same Chan et al. 14th paper. The best upper bound is into 2/3, but the lower bound is into the 1/2. Therefore, there is a huge gap between the upper bound and lower bound. It is natural to ask, what is the true complexity of dynamic range mode? In our work, we make a small progress towards answering this question. We show that the upper bound is not true. Specifically, we show a deterministic data structure for dynamic range mode that runs in worst case O tilde into the 0.656 time for both update and query time. The key idea in our work is to reduce dynamic range mode to some type of mean plus product problem. In the mean plus product problem, we are given two matrices A and B, and we are asked to compute for every ij the minimal value of aik plus bkj over all indices k. In a Williams et al. 20th paper, they show that batch range mode can be reduced to mean plus product of some special matrices. We will talk about batch range mode later in more detail. We show that dynamic range mode can be reduced to a data structure version of mean plus product. The data structure version we were referring to is called mean plus query problem. So it has an initialization phase and a query phase. During the initialization phase, we are given two matrices A and B, and in the query phase, we are given three parameters, ij and s, where I and j are two integers, and s is a set of integers. The data structure needs to compute the minimal value of aik plus bkj over all indices k that's not in S. So here, we are actually computing a single entry of the mean plus product of A and B, excluding a set of forbidden indices. Now, I will first review the batch range mode algorithm of Williams et al. 20. In the batch range mode problem, we are given an array of size n and n range mode queries, and we need to compute the answer for each range mode query. The classic algorithm for batch range mode runs in n to the 1.5 time, roughly, and there is also a matching combinatorial conditional lower bound. Here, combinatorial means that the algorithm is not allowed to use any algebraic techniques especially matrix multiplication. In the Williams et al. 20th paper, they show that if we indeed use fast matrix multiplication, we can get an algorithm that beats n to the 1.5 time. The first idea is to treat frequent and infrequent elements differently. For elements that appear more than n to the 0.499 times, we call it frequent, and for other elements we call them infrequent. Note that this n to the 0.499 parameter is not the optimal parameter for the algorithm. This is set so that we can beat the n to the 1.5 barrier. So to do some pre-processing for infrequent elements, we find all pairs ai equals aj equals x and create an interval ij whose weight is the number of occurrences of x in the subarray from ai to aj. So for instance, in this example, we first create all length 1 intervals of weight 1, and then there are 3 weight 2 intervals. And finally, there's a single weight 3 interval from the first 3 to the third 3. For our query LR, we first find the interval contained in the range LR that has the maximum weight. Then the mode of LR is exactly the element associated with this maximum weight interval. For instance, if we have a query of the subarray 3321, we find the maximum weight interval contained in this array, which is the interval from the second 3 to the third 3. Therefore, the mode for the query is 3. Since we only do this for infrequent elements, we will create at most n to the 1.499 intervals. Therefore, we can use some data structure to maintain them efficiently, and thus this preprocessing can be done in O tilde n to the 1.499 time, and each query can be answered in O tilde 1 time. The second idea is to pre-compute some range mode queries for some fixed intervals. We split the array into blocks of size n to the 0.499, and we pre-compute range modes between every pair of endpoints. So for instance, this array has size 16, and we split it into 4 chunks of size 4. We will pre-compute a total of 10 range modes, and here we show 2 examples of them. Let's first assume we already computed these range mode queries. Then, given a query LR, we first find the largest span of blocks this query contains. Then the mode of LR is either the mode of this span or one of the remaining elements. Since the number of remaining elements is at most twice n to the 0.499, we can enumerate each one of them and query the frequency of this element in this range. And finally, we take the best. Therefore, this part takes at most O tilde into a 0.499 time. For instance, here, the query is a range included by the blue parentheses. We first look at the largest span this query contains, and we already pre-computed the range mode of this span. Then we look at the remaining elements, which are 1 and 3. And finally, we determine that the mode is 1. In order to beat the n to the 1.5 benchmark, we need to perform an efficient precomputation using fast matrix multiplication. For simplicity, we split the array into 2 halves and only consider spans that cross the middle. For spans that lie solely in the left half or the right half, we can handle them recursively. We index the blocks according to their distances to the middle, and the indices for the left half and the right half are separate. For the left half, we create a matrix A, where aik equals the number of occurrences of element k between the ith block on the left and the middle. Similarly, we create a matrix B. Here, for instance, A11 is the number of occurrences of 1 in the first block. So there are 3 1s in the first block, and thus A11 equals 3. A21 is the number of occurrences of 1 in the first block and the second block, so it is 7. There are some nice properties about the matrix A. First, each column of A is non-decreasing. This is because AIK equals the number of occurrences of K in the first I blocks, and AI plus 1K equals the number of occurrences of K in the first I plus 1 blocks. For the second observation, let's look at the row sum of A. For the ith row, the sum is the total size of first I blocks, and for the I plus 1th row, the sum is the total size of first I plus 1th block. Therefore, the difference of the sum of I plus 1th row and the ith row is exactly the size of the I plus 1th block. Let's use lowercase n to denote the dimensions of matrices A and B. The first observation still holds. For the second observation, we replace 4 with the upper bound of the size of each block, which is n to the 0.499, and we can further relax it to n for simplicity. Then a theorem in Williams et al. 20 says that the mean plus product of such a matrix A and any other integer matrix B can be computed in O n to the 2.8599 time. Therefore, the precomputation takes O n to the 1.451 time, and thus the overall running time beats n to the 1.5. Now let's see how to adapt these ideas to the dynamic setting. The frequent-infrequent elements idea still holds. But now, the cutoff for frequent and infrequent elements becomes n to the 0.33. Also note that this parameter is not the optimal parameter, but this parameter can show an algorithm that can beat the n to the 2/3 benchmark. We need to lower the cutoff because if we insert or delete an element x, we need to update all intervals ij where ai equals aj equals x, and there could be n to 0.66 such intervals. Now, let's see the easier update, insertion. To handle insertions, we don't need to actually insert the new elements to the array. Instead, we can maintain a buffer and keep the newly inserted values in this buffer. To answer a query, we first compute the mode ignoring the buffer, and then we test whether each element in the buffer could be the mode. Therefore, this part takes O tilde into 0.66 time, because this is the buffer size. But note that we still have to put these elements back to the array at some point. So after every n to 0.66 insertions, we flush the buffer and recompute the precomputed values. The hard case is actually the deletion operation. Because it is hard to recompute the mode of a span of blocks after some deletions. For instance, here we precomputed the mode for this span. But if we delete several elements from this span, we are no longer sure what the mode should be. Therefore, we need to ask the mode of a span of blocks, ignoring some elements that are recently deleted. This is where the mean plus query problem comes in. As we can see here, the set S actually denotes the set of elements that are recently deleted, and we are asking the mean plus product of A and B excluding these recently deleted elements. So this is what we want. Our main lemma says that we can do this mean plus query problem efficiently. So the number of rows of A is the number of blocks, and the number of columns of A is the number of frequent elements. So that's why here is a rectangular matrix. The two observations for matrix A still holds, and our lemma says assuming these two observations, we can solve the min plus query problem quite efficiently. So we can perform initialization in n to the 1.31 time and query in n to the 0.66 time, as long as the input set S is not too big. This n to the 1.31 initialization time is better than brute force, because if you do brute force, we need n to the 0.34 times n to the 0.67 times n to the 0.34, which is n to the 1.35. And if we do query naively, then the query takes n to the 0.67 time. So this query time is also better than naive. On average, we reduce the initialization phase after every n to the 0.66 updates. So on average, each update only takes less than n to the 0.66 time. And therefore, using this lemma, we get a amortized time algorithm that runs in O tilde n to the 0.66 time. There are existing techniques that improves such algorithms with amortized runtime to worst-case running time. Due to time constraint, I won't be able to show you the whole proof for the main lemma. Instead, I will show you an easy example of a min plus query type problem. So in this example, both matrices A and B are n by n matrices, and their entries are positive integers less than m. In this case, the min plus query problem between A and B can be solved in O tilde m times n to the omega initialization time and O tilde size of S query time. Here we have an example matrices A and B where m equals 3. Let's first consider the classical algorithm for computing the min plus product of such A and B by Alon et al. 97. A key step in their algorithm is to create auxiliary matrices A' and B', where A' ik equals to n plus 1 to the power of aik, and B' kj equals to n plus 1 to the power of bkj. Here we create A' and B' for the example. The Alon et al. 97 paper noticed that the matrix product A', B' actually determines the mean product of A and B. We noticed that A', B' actually determines more information. Specifically, A', B' ij determines the number of k such that aik plus bkj equals a specific value for any specific value. For instance, here, A', B' 3, 3 equals to 2 times 6 squared plus 2 times 6 cubed plus 6 fourths. Therefore, the number of k such that A3k plus bk3 equals 2 is 2, and etc. Note that to compute the matrix product A', B', it takes O tilde m times n to the omega time, because every entry of A' and B' are integers with m log n bits. Then we can write down this information to an array L for every pair of ij. To answer a query, we try to remove every k in S from the array L. For instance, here, let's say we got a query I equals 3, j equals 3, and S equals to the set 1, 2, 3. First, we remove 1 from the array. Here, A31 plus B13 equals 2, so we decrement L2. Then, 1 plus 2 equals 3, we decrement L3. And finally, we decrement L2 again. Now, the earliest non-zero entry of L is L3. Therefore, the answer to the range model query is 3. Of course, we need to roll back after each query, but this does not this does not change the time complexity. To maintain the array L efficiently, we can use any balanced search tree. To give a proof for the mean lemma, we adapt the algorithm of Williams et al. 20 to work in the mean plus query setting. Hopefully, the previous example gave you some intuition how this adaptation might look like. There are still many more open problems about dynamic range mode. For instance, we still don't know the true complexity of dynamic range mode. Can we improve the current algorithm further? Second, our algorithm uses faster matrix multiplication. However, if we consider combinatorial algorithms, the lower bound and the upper bound still have a huge gap. So can we get a faster combinatorial algorithm, or can we improve the combinatorial lower bound? And finally, it will be interesting to see the mean plus query framework used in other settings. Thank you for watching.